Okay, now we continue our conversation in chapter 14 with this question. Is water an acid or a base?
Base.
Let's address that one. Is water aqueous? Traditionally, we're going to say no. We don't consider water aqueous because it doesn't dissolve in water per se. It is water. So it's not really aqueous because it is the solvent. Now, is it an acid or a base?
It's a base.
The answer is yes. Here's how we get that. What does an acid do? An acid is something that, what's that?
Dissociates the
Okay, so it's a if we use the language of Bronsted-Lowry, an acid is a proton donor. Okay? Proton donor. Okay? Can water donate a proton? Sure. Okay? What is a base?
proton.
Proton acceptor. It's something that can accept a proton, right? Okay. Depending on what else is present, or in fact if there's nothing else present, water can do both of these things. And we have a word to describe a substance that can act as either an acid or a base. That word is, no. Water is a good example, but we have a wider term. The term that we use is amphoteric. A-M-P-H-O-T-E-R-I-C. Amphoteric. Amphoteric means that the substance can act as either an acid or a base. Water is the most common, most familiar example of a substance that can do this. Ammonia. Your book actually talks a little bit about that. Ammonia, in its pure form, can split into ammonium ion, NH4+, and what's called amide ion, NH2-. Just like water can split into H+ and OH-. Okay? So, water can act as either an acid or a base. This ends up becoming important as we continue on our conversation in this chapter and start talking about acid-base reactions in an aqueous medium. Okay? Now, the key to understanding this is knowing that water dissociates. Now, we've talked about dissociation of an acid, how if you mix an acid with water, it splits into ions. Water auto-dissociates. That is to say, it will split up all by itself. Even if all you have is just pure water, distilled water, it will still split up into its ions. And that auto-dissociation looks something like this. There's two ways you can represent it. You can represent it this way. That's one way you could do it. Okay? Or the other way, that's maybe a little more precise, you could do this. Okay? Yes?
So do single hydrogen ions exist by themselves, or is it always going to be hydrogen?
We think of it more specifically this way, but it's okay to represent it this way because this is just the same as this, except you're not including the solvent. Really, this is just a hydrogen ion with a molecule of solvent attached. Now, if you want the really complex answer, the way that this really happens is something like this. Usually there's about 9 water molecules around each hydrogen ion. At least that's what my professor told me. But that makes the stoichiometry a real pain in the butt. So we're okay to use either of those. And which one we use may depend on whatever else we're comparing it to. If we need to take into account that water is a part of the reaction, we'll probably use this one. If we don't care, if the water is not actually a part of the reaction, if it's just the medium the reaction is taking place in, then this one is fine. All right. So, these both represent the auto dissociation of water. What does the auto mean? It means it does it by itself. You don't have to put any energy into it or anything. When you have pure water just sitting around, it will automatically begin to do this. Now, does that mean that there's acid in every drop of water that you drink?
Yes.
Yeah, there is. But there's an equal amount of base, too. So it kind of balances out. It does balance out. Now, the degree to which this happens is a matter of some importance. Okay? So, at 25 degrees Celsius, they have determined the following for pure water. Let's make that distinction. Pure water. Okay? 25 degrees Celsius, pure water shows this. Concentration of hydrogen ion is equal to 1.0 times 10 to the minus 7th molar. Times 10 to the 7th moles per liter. That's a comparatively small amount. It's not a lot to really get worked up over. All right? So, using your powers of deduction, tell me this. What would the concentration of hydroxide ion be? Why? Yeah, I mean, stoichiometrically, you get one of these for every one of these. They have to be the same amount. That's true. Concentration of hydroxide is 1.0 times 10 to the minus 7th moles per liter at 25 degrees Celsius. This becomes one of our assumptions. We will assume that, unless otherwise specified, our reactions are taking place at 25 degrees Celsius, which is a little warmer than it is in here right now, but you know how our lab gets sometimes. All right. That's the auto dissociation of water. Now, let me encourage you to learn these two numbers, or maybe learn that number twice, since it's really the same for both things. It's going to become handy here in just a moment.